When analyzing an object on an incline, we often recognize that the friction would be the reason why the object doesn't slide down the hill. And in order to do this, we need to be able to resolve vectors into perpendicular components that will match a rotated frame of reference. So to begin, with a mass m sitting stationary on an incline at an angle theta, the first thing we're going to do is we are going to rotate our frame of reference. So instead of the typical vertical frame of reference that we've said, I'm going to set perpendicular to the surface as positive y and parallel to the surface going down the hill as positive x. This is a new frame of reference that's relevant to the surface. And we do this on purpose because looking at the object, we know that the object is pulled with weight going straight down. This is your f of g component of force, right? That force is straight down, but when it is pulled straight down, due to the orientation of the surface, the normal force always acts perpendicular to the surface. And so a result is that the normal force does not align with f of g. And we know that this is true because if this object was round and we put it on a hill, no matter what the normal force, the object rolls down the hill. And this is true because f of g is not completely canceled out by the normal force because they're not in opposite directions. And so in order to analyze how the friction is being generated by the normal force, right, because don't forget, f of f is a function of the normal force, mu times f of n, then what we need to be able to do is find the values that match up to these various directions. And so the key, as I mentioned briefly in a previous video, is to set f of g as a resultant vector that's comprised of two perpendicular component vectors that point according to my new frame of reference. And so fg in the y direction points in this direction, down from the surface along a perpendicular. And then f of g in the x direction would go parallel to the surface. And so for a rolling object, if this were round, then f of gx is the reason why it rolls down the hill, because it's perpendicular to the vertical forces and has no opposition, and therefore is the reason why it rolls down the hill. But a solid object, like this, a flat object that's not round, has an additional horizontal force acting this way, so-called horizontal, up the incline, resisting this f of gx and preventing it from rolling down the hill. And so what we see is that we take f of g and resolve it into f of gy and f of gx in order to analyze the actual actions. And the key here is being able to locate an angle within this triangle to resolve into f of gy and f of gx. And what we have typically is the angle of the incline. And so that would be this theta here. And so if we look at the geometric triangle that's traced out here with f of g to the bottom base of the incline, this triangle is similar to this triangle here. And so if we analyze carefully, we'll see that going to this top corner, the angle in this top corner of this triangle would be 90 minus theta. And then also notice that the surface to f of gy are perpendicular, which means that if they are perpendicular and this is 90 minus theta, then this angle must be theta. And so it's important to note that in an incline problem, when rotating the frame of reference, the top angle in my f of g resolution is the angle that the incline is so set at, which means that f of gy is the weight force times the cosine of theta, and f of gx is the weight force times the sine of theta. This allows me to resolve the weight into perpendicular components that match the frame of reference. And so then I can analyze the sum of the forces in the x direction as m times ax, and the sum of the forces in the so-called y direction as m times ay. And so what I have is the sum of the forces in the x direction as being f of f in the negative direction and f of gx in the positive direction. So I have f of gx minus f of f yielding a mass times an acceleration in the horizontal plane. And so, of course, if f of gx is greater than f of f, then the object would slide down the hill. If f of gx is matched by f of f, then the acceleration is 0 and the system holds stationary. And so you can imagine that as I increase the incline, right, and I go from theta being relatively low to theta being relatively high, what you see is that as I grow theta, theta increases f of gx because more of the weight force is aligned with down the hill. The more of the weight force that's aligned down the hill, the more likely it is to overcome the friction. And since the friction is a function of the normal force, and the normal force is a function of the vertical forces, as I increase the hill, I am decreasing f of gy. Decreasing f of gy decreases the normal force and therefore causes the friction to be less overall. Because in the summation of the vertical forces, I have f of n in the so-called positive direction, and I have f of gy in the so-called negative direction, equal to m times ay. And so as I tilt the hill up and up and up and up, the angle decreases the vertical force. What we also have to recognize is that the friction force is a function of mu, and mu has two possibilities. It could be stationary, it could be kinetic. So in this particular example, I assumed the mass was holding stationary, but we can imagine that if I took the mass and started at the bottom, and so instead of the diagram I have above, although the directions of the force, most of the forces would be the same, if I had a mass m and it was moving already with some v, then I would analyze according to the motion, which means that the free body diagram would yield a friction force that would be down the hill in this particular case. And so we would have an f of f down the hill as the object slid up the hill. But then once it got to the top of the hill, we would expect that due to friction and the just natural state of the deceleration, that it would get to the top and v would be 0. So here we would analyze this f of f using mu k, because it's sliding. Here we would change to mu s, which means that the friction force will be different based solely on the action that's happening within the system. But if this friction force value isn't high enough to keep this object stationary, then again it would slide back down, and so we would expect it to then reverse course and head back down the hill. And so heading back down the hill, then we'd have to be careful to note that now the motion has reversed, and so the friction force is now in the opposite direction. This friction force, again, is based on mu k, and so we have the same value as it was going up in the opposite direction, and a completely different value resisting the motion, right, which in this case, directed down the hill, would mean that the f of f in the static case is up the hill, preventing the object from sliding down. And so we would see that here we're back to looking at it as the f of f resisting f of gx. Whereas here, on the way up, f of f is actually working with f of gx in order to slow the object down in a shorter period of time than it would if it were a round object just rolling under its own power. Once it gets to here, then of course it's coming back down due to f of gx, and f of f is resisting that, causing a lower acceleration than if the object were just rolling. It takes a little practice to get used to this diagram, but you should definitely practice drawing the incline diagram and resolving f of gx into f of g into f of gy and f of gx, so that you can make these assumptions about the Newton's second law. Take your time, draw this picture, draw it big enough that you can see these vectors, and compare. And then it's not a bad idea to go ahead and compare this to the same scenario where it's a ball rolling. With a ball rolling, we will not have the friction values, but you will still have the f of g pointed down that can be resolved into the f of gy and f of gx values. And so it's a nice comparison to the diagram that we saw above.